the strategy of the factory ECU is way ahead of what we're seeing in aftermarket ECU. You have been mentioning MED9. If you look at top grade aftermarket ECU, it's not even close to that. And keep in mind that it's an ECU that is 15 years old.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we've got Aurélien joining us from bFlash. Now, bFlash is a supplier of reflashing solutions for primarily late model European vehicles, and this is an area where there is a huge amount of misinformation, or maybe just a lack of information in general. And I know from running my own performance workshop for about 13 years, the European tuning market was one that I was always a little bit maybe put off and afraid by, because a lot of the European tuners that are specializing in the likes of Volkswagen, Audi Group, maybe Mercedes-Benz, BMW, are using products like WinOLS, which is a binary editor for finding and defining maps in a raw binary file. To me, that is not tuning as such, and it's a very different skill set. So at the time, that was an area that I chose purposely to stay away from. But obviously that European vehicle market is massive, and people with these cars obviously want their cars to perform better as well. So there are more and more solutions coming out. That bFlash product that I mentioned, this is an interface that allows you to read and write the factory engine management system. You still need another solution in order to actually edit the maps. It's not a map editing software, and we dive into what all of that means as we go through our interview with Aurélien. Now, I just want to mention here as well that while there is a difference in the skill sets between what we need to understand and know in order to be able to tune a factory engine management system and what we need to understand in order to be able to find and define these maps, it is not an insurmountable task. I've spent the last few months learning the ins and outs of WinOLS for an upcoming WinOLS training course, which may be of interest to those who go through today's chat with Aurélien and want to learn how to do this for themselves. This is a fairly wide-ranging chat, though. We talk about how he got involved in tuning in the first place back in the early days, burning EPROMs, the early days of standalone engine management systems. We talk about modern engine management systems and why they are so good. And I think particularly for those tuners coming from the aftermarket standalone industry, often we look at factory engine management systems and think that they are inferior. The reality is very, very different. These are incredibly sophisticated engine management systems, and the advantage that they have often over an aftermarket standalone is that everything that they do is focused on operating a single type of engine to the absolute best of its ability. On the other hand, if we look at an aftermarket standalone engine management system, that same ECU may need to be able to reliably and comfortably operate thousands of different engines. So it's a very generic product. Nothing specifically wrong with that, but there are very different sort of targets or applications between standalone and factory engine management systems. We also learn in this interview about how a factory torque-based ECU works, how that differs from a conventional standalone ECU that most aftermarket tuners would be more familiar with. And then we also talk about why this is an advantage, particularly as cars become more complex. Obviously, as time goes on and cars become more complex as well, the other aspect is that a lot of OE manufacturers don't really want us in the aftermarket making modifications and changing the tune. So there's a lot that goes into modern security systems. And we find out that, don't worry, there is still a ray of hope in the future, and at least as far as bFlash are concerned, we will still have a option to tune late model vehicles or current model vehicles for a number of years to come. So I know that's something that a lot of people are worried about. OE's basically making it impossible for us to tune. So it sounds like that's not something we need to be too concerned about anytime soon. Now, before we get into our chat, just for those who maybe are new to High Performance Academy, we are an online training school. We specialize in teaching people how to tune factory and aftermarket engine management systems. We also cover topics including performance engine building, wiring, harness construction, race driver education, data analysis, and even topics on fabrication as well. You can check out all of our courses at hpacademy.com/courses relevant to today's topic. Our Efi Tuning Courses, though. These include our Efi Tuning Fundamentals, and regardless whether you're reflashing a factory engine management system or you are tuning an aftermarket standalone, this will teach you the fundamentals of what is going on inside of the ECU and inside of the engine. You'll learn why an engine needs a specific amount of fuel and how to optimize the ignition timing. Moving on from that, and again relevant to today's topic on reflashing, we have our practical reflash tuning course, which will teach you how to reflash essentially on any platform and on any engine. It doesn't matter, because the principles of how the engine operates essentially remain the same. Now, I know particularly on a complex current model factory engine management system, this can seem somewhat overwhelming. What do you do first? Where do you get started? Well, what we've done with the Practical Reflash Tuning course is broken the process down into the HPA 6-step process. And by doing this, each of those individual steps is relatively quick and easy to complete. In no time, you've got to the end, you've got a properly tuned engine that's delivering great power, great torque, and most importantly, great reliability. We will put a link to all of those courses in the show notes, and as a podcast listener, you can also use the coupon code podcast75. That's going to get you $75 off the purchase of your very first HPA course. All right, enough of our introduction. Let's get into our interview now. All right, welcome to the podcast, Aurélien, and I will apologize straight off the bat for my very poor French pronunciation. I'm channeling my best inner French, but of course I'm not very good at that, so I will apologize right at the start here. But welcome to the podcast, and thank you for joining us. Now, I want to get a bit of background history on you and how you got involved with tuning and specifically reverse engineering of factory engine management systems, because it is, let's be honest, a fairly unique and diverse skill set.
Reverse engineering is something I started to do 5 to 10 years ago. Initially, I went into that field because we were stuck with the last test control units. We were not able to program them, tune them because of new securities. I initially come from a tuning background, so I was mostly doing calibration as a calibration engineer. This is my training, what I've been studying. At some point, we had to come up with new solutions, new perspectives, because conventional flash tools will not able to make progress on the platforms we're interested in. And also because, when you tune a car, you have a given point of view on what you need, what you want to see, what you want to do with the tool. Like, for example, the diagnostics, the data logging, you know exactly what kind of information you would like as a feedback. So we decided to go on that route and try to come up with new solutions and innovative solutions.
Let's roll back a little bit, and before we get into talking about reflashing and reverse engineering of factory engine controllers, let's talk about your background in terms of just conventional tuning. And I'm going to guess you started out, like most of us do, probably tuning aftermarket standalone engine management systems. You mentioned training in that. How did you learn those skills, and maybe what systems were you tuning?
So initially, I did not really start on aftermarket. I started on aftermarket more or less at the same time. I initially started with Subaru in Evo. So it was the OpenECU era, the ROM Raider era as well. I have been playing also a bit with Link ECU, Motec ECU, so mostly that kind of brand. So with Japanese scene, which was quite popular at the time, and clearly the German tuning, like for Volkswagen, Audi, and all that kind of brand, it was very secretive, and you could not get involved in that market very easily at the time.
Okay, let's talk about the Japanese market, because that was a big part of my professional tuning business as well. We are lucky in New Zealand to get a lot of Japanese domestic market imports, so we're well known with the Evo scene, and there's hundreds and thousands of Subaru STIs and WRXs all through New Zealand, so they were a very popular and cost-effective platform for tuning. Much like you, I was using, by the sound of it, the same tools. In terms of how that works, just for those who are listening and maybe don't understand, you're using a interface, generally the Tetrix cable that connects to your OBD2 port, open source software. There was some commercial software available as well, but most people using open source software such as ECU, Flash, ROM Raider, etc. for logging and for actually reading and writing the ROM from the ECU. The key part though here, which differentiates, I think, reflashing of a factory engine management system to aftermarket, is when we pull that file out of the ECU, essentially it's garbage to us, isn't it? You require a definition to actually say, well, at this address in the file, we've got a fuel map or an ignition map or whatever that may be. So we're essentially blind to being able to make tuning changes without that definition. Is that a fair way of explaining things?
So yes, the big advantage of aftermarket ECU is that you don't need to build any definition, you don't need to do any reverse engineering, you just, wire it and then you can, you're free to play, free to calibrate. So it's easier in some way, but it's also, you start from the scratch. You don't have any, sometimes you have base maps, but you're clearly not using a factory product with all the details and time spent by the OEM into calibrating it. Indeed, when you're working on the stock ECU and when you read it, or write it, you get a binary file that is, as you call it, a chunk. It's all garbage, and you need to figure out in the code what is each byte, what is each map, how it works. It's clearly taking time, but the open source community have, a lot of resource on Subaru and Evo. There is tons of resource online, people that are helping each other to find maps, and did a very great job. So, and I think it went even better after time. We started to see people that were making custom patch, add-on features. So the stock ECU was really a capable platform at some point.
I don't want to sort of derail the conversation too far, because we do want to spend a big chunk of time here talking about the European market, because on this side of the world, growing up and tuning, that, as you mentioned earlier, it was very secretive, and there weren't a lot of options available to us as general tuners to break into the Volkswagen, Audi, BMW market, for example. So we're going to talk about that, but let's just sort of continue a little bit further down this rabbit hole on the JDM product, because it is one that I at least know reasonably well. And you're right, that there's this big enthusiast network, forums, etc., with a lot of people doing the heavy lifting of building what I call this definition file, which, as you say, it sort of takes that raw binary file and says, at this address we've got this map, it's this size, here are the axes. So what that means is, for us, if we've come from an aftermarket ECU background, that software that the aftermarket ECU provides kind of takes all that hard work out, because you click a tab and there's your fuel map, click another tab, there's your ignition map. It's easy, and it doesn't work like that in the OEM world. So we've got these people doing that heavy lifting, providing these definitions. But one of the problems I found, because a lot of that work was done primarily in the US, just because that's the biggest market there's more people there, and there's quite significant differences most often between the controllers that were fitted to the European and US domestic market models versus the Japanese domestic market models. So quite often we would get a car where I struggled to get a definition for, and then we're stuck. So were you in that situation? Were you sort of starting to reverse engineer the controller yourself, or were you always in a situation where you had good definitions to work from?
No, it was exactly the same situation. So there was a lot of very good definition for the US models. And when you come to GDM models, AUDM model, and EDM models, it was a lot more limited. But you meet the right people, the right enthusiasts that are spending the time doing the job, and that's all you learn. But clearly there is a big amount of work that needs to be done so you can properly define a file, properly define a ROM. But once you have, like, let's say one example, like as I can call it, like from the USDM box code, it's quite easy to find the information you need in code and port it to the new box code. It just takes time. So really the big hard part is actually doing the initial reverse engineering and figure out how it works. That's the real hard part.
So to paraphrase there, what you're saying is once you've got that initial proper definition, you know it works, to go to a different ECU, a different ROM, you're saying basically those same maps will be available, but maybe they're in a different address, and it's a case of just redefining whereabouts to find that particular map?
Yes, that's it.
Okay.
Most of the time, that's how it works.
All right, a couple more questions just on this, because you mentioned patches, and again, probably a lot of people listening won't understand what that terminology means, but what's your sort of definition of a patch, and how does that kind of work at a firmware level, an ECU level? What's it doing?
So a patch is actually a change in code. So it's not a change in the calibration, but rather in the way it functions. So you are actually adding new code that gives you new features, for example, launch control or flat foot shifting or all that kind of features, or map switching, for example. That's one kind of patch. It actually is a feature that is not designed in the existing original code because it's either not needed by the OEM or, not wanted by the OEM. And we just spend some time to create a new function to add the function we want. It's the case for many other things. For example, like FlexFuel. It's something that is very common right now in modern ECU because you have a lot of FlexFuel vehicles from the factory. But 15 years ago, it was clearly not the case. So many people had to actually make code patch to enable that kind of feature, such as flex rate sensors.
With this sort of work, creating a custom patch, custom software features, is there any limitation based on the controller that you're working with, or is it really just down to the imagination of the person writing that piece of code?
There is indeed some technical limitations. For example, you have the speed of the CPU of the control unit. You have the space. Like there is a given amount of ROM space, and once the ROM is full, you cannot just put more maps. I mean, you can perfectly imagine that if you double the number of maps, at some point you will be limited by space. But apart from that, it's just from the imagination of the people that is programming. There is also other technical limitations, like for example, some ECUs will not have an extra input you might want or need, but we can overcome this limitation. For example, we can come with a new solution, such as something that is connected to CAN bus, and then you just read the message that is sent, or do the exact opposite, which is sending a message on the bus, so you can actually activate that function.
At a much lower level that avoids the complexity of CAN bus messaging. I remember on some of those Japanese vehicles that you're talking about there, it was common to perhaps bring in an external wideband air fuel ratio controller over something like maybe the factory rear O2 sensor input, which wasn't strictly essential for normal operations. So I guess there's usually some ways around it, but of course, you're limited to that factory header pinout and what's available. And of course, not all inputs are available for every function we may want to potentially connect. Now, just taking that to its extremes, would it be possible, therefore, to essentially completely override how the factory did everything inside of that controller and maybe essentially rewrite the code to look a bit more like a conventional speed density style aftermarket ECU? You mentioned the likes of maybe Link or Motec. Is that possible if someone wanted to go to the trouble?
Yeah, it's absolutely possible. In fact, you could actually rewrite the Onto firmware and just make your own maps for everything. If you just spend the time on it, it's going to take a lot of time, but an ECU is just a piece of hardware, and you can load the software you want and include all the features you want, so you can clearly change completely how it works. There is many people that have been including for Subaru and Evo a speed density patch where they either replace the map sensor or emulate the map sensor to be more exact. It's something that can be done.
Okay. Now, it sounds like at some point you sort of got strayed away from using the existing definitions, or maybe those definitions weren't complete enough. And this is where I'm guessing you sort of crossed from being just an engine tuner. And I don't mean that in an insulting way, but from just working with an existing map that you could see, and you had to actually start diving into the matrix, for example, and actually start to reverse engineer that raw binary file and start finding maps. And this is the bit that I'm interested in, because as I see it, and I've been on both sides of this now. I am just at the very early stages of learning to use WinOLS, which is kind of the gold standard for reverse engineering factory engine controllers at the enthusiast level. It's a very different skill set from that of just engine tuning. So I'm interested, was there something in your background around computer systems engineering or coding, or did you learn this skill set out of necessity because you wanted to be able to expand what you could do with tuning?
It was mostly by necessity. Just like you said, most ROMs for Japanese car were defined for US models, and when you work on Euro models or other models, let's say, there is not all the definitions you want, so you need to spend the time. You mentioned WinOLS, but there is not just WinOLS. WinOLS is one tool. There is other tools. WinOLS is one software that gives you a visual representation, so it's very practical for matching patterns. But when you really want to understand how it works, you definitely need to spend some time in the code, in the raw assembly, so you can actually read the instruction sets and see what it does. That's two different approaches. One is very fast. As I said, when you have a reference binary, you just need to match the pattern. It's going very quickly. When you need to do the initial job, which is really finding the maps, the structure, how it works, what is the size, what is the location, then you clearly need to do it by code. With experience, you always find a way to do it just with the pattern, because all maps have a given shape. If you look at an initial timing map, for example, it will always have that shape that is rising with RPM and decreasing with load or something like that. Of course, you were going to see bumps, but the general tendency of the map is going to be something like that. Same goes for enrichment. It's more or less the same for every big major maps. They all have that physical shape that is related to how an engine works and what you need to do with it. And so once you are used with the pattern, like the shape of the map, you can just quickly see it in the dump. You look at the pattern, you're like, okay, I don't know what initial map it is, because maybe there is 20 initial maps, but this is one initial map.
I'll just back up a little bit for those who are maybe starting to get lost. And unfortunately, of course, using a podcast, we don't have the benefit of being able to show pictures of what you're talking about, but essentially what you're talking about there is the patterns of these maps. So when we're using a binary editor like WinOLS, it gives us the ability to view a two-dimensional sort of graphical representation of the binary file. And sort of, first of all, OLS will by itself find what it thinks may be a map, which on face value seems like a great function, but in reality, it's probably going to miss a bunch of maps, and it's also going to find a whole bunch of maps that are probably essentially of no value. But by scrolling through what is quite a large binary file, we start to sort of recognize these patterns, as you've said. And when you've done enough of it, you sort of can see, oh, that pattern there, this will be EGR or ignition or driver's wish or whatever that may be. And you can sort of then define that more correctly or more specifically. There's still a few steps in there as well, because the numbers for, let's say, throttle position probably in that raw file aren't going to be something we'd recognize as 0 to 100. So we've still got to apply scaling, likewise to lambda or ignition timing. So there's a little bit to it, but as you say there, that pattern recognition is really the key element. Someone who's done enough of this can scroll through that raw binary file and go, yep, here's the key maps that I know for this controller. I'm probably going to need to be able to do a basic, let's say, a stage 1 calibration on it. Now, you've also mentioned this other aspect here, sort of getting into the actual code itself. So are you talking here more about understanding from the code the how would I put it, the steps the processor, the controller is going to go through from input A to output injection, millisecond pulse width, and ignition timing? Is that sort of what you're getting at there?
Yes, exactly. So if you look at the full process, let's say for ignition timing, for example, you will have the base map and maybe interpolation between a few sets of maps, like let's say high octane, low octane, for example, and then you will have some correction behind, like let's say air temperature, coolant temperature based, whatever, knock correction, all of this, and you will just see it in the code, like, okay, it's doing that, then that, then that, and each new step you will be able to follow how it works, and that's clearly not something you can detect just from the pattern. You really need to understand. Otherwise, you cannot just get the order. You don't know, for example, if one map is the maximum value or the minimum value. It could just be guessing. Once you actually do the reverse engineering in the code and you look at what the instructions are doing, you can see if it's an adding value, a subtraction value, a maximum value. It can be many things, but at least you see it from the code.
So this takes you from a basic understanding where you might have, as you said, 20 ignition maps, but then understanding which of the ignition maps will be active under a certain condition, and then, as you've mentioned, what adders or subtractors, multipliers may be working on top of that map. So building up that full comprehension, so you know exactly what the steps are going to be to get a defined outcome. Yes,
but once you do enough ECU, you will see that they always have the same logic. It's just like they extend the logic, they improve it to add new corrections and let's say different way to achieve the same results. But it's an iterative process. I mean, it's just like aftermarket ECU. You have all the definitions, but each new revision, like there is a new firmware, it releases a new feature, and then you have that extra correction or something like that. And it's exactly the same process in an OEM ECU.
All right, so if we talk about sort of the European tuning market, and we've got the likes of Bosch and Siemens as two of the controllers, which are pretty popular. That one controller, let's say Bosch, for example, could be used across a wide range of different vehicles and models. And of course, as time goes by, Bosch learn more and add more functionality to their controllers. But is this sort of, how would I put it, like a family resemblance to the Bosch MED series of controllers that dates back to the earlier, like we've got a MED 9.1 and a Mark V Golf that we're doing some work on at the moment, up to something more modern. Is that how that works? Or if you take the most modern Bosch controller, it looks nothing like the older stuff?
Well, if you follow all the revision, you will see how it evolves. But if you go straight from MD9, let's say, to MD1, which is the latest one, then there is a very big gap. For example, let's say the boost control in the very early version, so like ME7, it was like something with a boost set point and just a basic wastegate duty map and a PID. And all of that have been evolving over time. They have been complexifying this, like adding new dynamics in the PID. And at some point, they just completely removed the wastegate model, and they actually put a physical model of the turbine and the compressor. And it took us a lot of time to understand it. They actually started this on the Max, on the Golf 6. And because the Golf 7 was a Siemens ECU, it was also, again, completely different. But you can, I mean, if you look at other Bosch, like from other brands like Ford or things like that, you will see that there is a common structure. And once you understand the structure from one, then it helps you understand the structure from the new manufacturer or new supplier. And it's an iterative process. It's clearly not something you can get otherwise.
Sure. Okay. So my understanding as well is when Bosch supply a controller to the likes of Volkswagen, Audi Group, they have their base strategy of how that controller for a specific generation will work, but then also there'll be consultation with Volkswagen, and they may want some other functionality or features added in. So then they supply that same controller. I think you mentioned Ford there, and again, Ford may want their own aspects. So there's subtleties and differences between the same controller on a different manufacturer's platform. Is that correct?
That's more or less the idea. So, for example, MD9 was installed on Ford 2.5, which is also a Volvo engine. It was installed on VAG, of course. It was installed on Ferrari. All of this have like a real common root, and then each one of the manufacturers have some very specific functions for their own requirements. Like, for example, the diagnostic or the reprogramming, it's completely different from one brand to another because each one has their own specifications, but you can clearly see a common root.
Okay. All right. I'm interested to get a bit of an understanding from you on torque-based ECU operation. So this is something we don't see very much in the aftermarket world with standalone ECUs, but really it's the basis of every modern OE ECU. So can you tell us how a torque-based ECU works and how that differs from what we may be used to in the aftermarket standalone world? So
the main idea is that you convert your pedal requests into a torque requests. And on the top of that, we'll input every other accessories, like, for example, the AC, the whatever. And we'll add all of that into a physical model that will say, okay, this is exactly how much torque I need to request from the powertrain. Once you have the torque set point, it's converted into some sort of air mass you want, so air load, that will actually provide you a bit later in the calculation, a boost set point. So the big story is you go from the driver wish, or what the driver wants as a torque, and you convert it into some sort of boost pressure or air load. And the big idea behind all of this is that the control is a lot more precise because, for example, if you turn on the AC, it's still going to produce the same torque. And in case of an automatic gearbox, if you want to do a perfect shift, it will just set exactly how much torque reduction it wants rather than just applying a fixed retard. Same goes for traction control like ESP and all of this. It's going to be a lot smoother because you're actually transforming a system with just like a PID gain or something like to control the traction into a linear system where the linear input is actually the torque.
All right, so a bunch of stuff to go back and no, that's good. But let's dive a little bit deeper. I think that's probably a good high level understanding of it, and I think probably an easy way of kind of understanding maybe why manufacturers have gone this way and where the advantages are. You mentioned the automatic transmission, DSG is another one. So to get that smooth shift, the DSG transmission control module is going to talk back to the ECU via CAN and say, we want the torque to be reduced to X, and then it's going to wait for that torque reduction to occur before the shift completes, and then it will say to the ECU again, all right, we can go back to full torque or whatever the torque was before. So that very accurate control and the ECU being able to report that torque is very important, particularly with DSG and automatic transmissions, to get everything to be nice and smooth and seamless across those shifts. And I think in days gone by with conventional manual transmissions, we didn't need that level of control that we now do. So that's one aspect. The other one with the traction control. So, I mean, in a conventional traction control system, we're generally relying on fuel and ignition cuts and percentages of cuts, which can be quite harsh. Am I right in saying now that the controller can ask for a specific reduction in torque, and then the ECU can just provide that? Is that what you're essentially saying?
Yes, that's the idea. So if you mentioned, like, for example, manual, but let's speak quickly of an aftermarket ECU. In the past, when you do traction control, you were like applying let's say an initial retard based on let's say how much the wheel is spinning. The problem with that is it's not linear. I mean, -2 degrees of timing versus -4 degrees of timing will not result in the same torque reduction. Same goes for the cut with the cylinders. Height of the cut of the cylinder is very linear because it's proportional to how many cylinders you cut. The problem is a non-linear system will not behave nicely in terms of regulation, because a system needs to be linear so the proportional gain can actually do the job as expected. And when you have a torque system, you can just say, okay, I want you to reduce the torque by 60 Newton meters, and it will reduce by 60 Newton meters. And if you want double of that, it will just handle all of the timing, all of the F path behind, and actually produce double, and not just double initial timing.
A couple of things I'll just again clarify or expand on there. You're talking about retarding the timing 2 degrees versus 4 degrees. It's not the same, and hopefully sort of people listening might have a understanding. We've done this a bunch of times in our webinars where we do what's called a spark sweep test, where we hold the engine in a fixed load and RPM and basically run the timing from 0 degrees through to 50 degrees, and you kind of get this graph that starts to climb really sharply, and then as we get closer to MBT, it kind of flattens off. So maybe, let's say, for example, at a fixed point, MBT maximum brake torque timing might be 28 degrees, but we'll find that there's this plateau across from maybe 20 degrees to maybe 35 degrees, where the torque might only change by a few percent. But once we get outside of that range, it kind of falls off a cliff on either side. So that's that non-linear aspect which you're talking about. So I just wanted to clarify that for those who maybe haven't seen one of those graphs. Hopefully my verbal explanation is good enough to get a bit of a grasp for it. Now, the other aspect I wanted to just ask about here is, it's all well and good. Okay, you say I want a 16 Newton meter reduction or a 32 Newton meter reduction, and the controller's going to achieve that. What are the options available, and how does it decide on what to do in order to get that reduction? Because we could close the throttle, change boost, timing, etc. So yeah, how does it know which of those levers to pull essentially?
The main concept is, I will speak for most ECU because there is, of course, some slight variation based on the generation, but the main concept is that you have what we call a slow path and a fast path. So the slow path is all that is related to the air loop, so boost pressure, throttle, because it takes time to build boost pressure or reduce boost pressure. It's not instantaneous. And the fast path is the initial timing, because, you can retard the timing for the next convention cycle. So it's going to be extremely fast. It's actually the fastest you can go. The idea is we'll target the slow path for the long run, and for the instantaneous reduction or increase, we'll use the fast path. It works for torque reduction, like during shifts, but it also, or traction control, but it also works like for idle control. If you just need to change your set point from 1000 RPM to 1200 RPM, it will first play on the initial timing to try to immediately raise the the RPM. Same when you push the AC button, it will first go with that and then move slowly with the throttle and the air loop.
Now, in terms of that timing that you've just mentioned there for, as you referred to it as the fast loop, if you want a very instantaneous change, I guess the options available are a retard initially and a cut if you need dramatic changes. Now, we've already talked about the fact that the relationship between torque and our ignition advance versus MBT is not a linear one. So if the factory controller is still doing this retard, does that mean that it has a built-in model of the relationship between timing and MBT and torque?
Yes, absolutely. So in all ECUs, all modern ECUs, let's say, you have at least two sets of maps. So one set is the map that you're really using, which is the run-in map, let's say. And you will have what we call the optimal ignition timing, which is the MBT. And it will all the time compute the delta between the two, so the difference. And based on that, it will know exactly where it is on the curve for the MBT, so the one you described earlier with the plateau and then the straight line. And it will constantly compute what we call an ignition timing efficiency, with 100% efficiency being the MBT. It will know exactly how efficient is the ignition timing, so it will be able to adjust and compensate for a reduction or an increase in timing at all time.
Yeah, all right, that makes sense. Now, another aspect with these torque-based ECUs that is probably a little bit foreign to those coming from the aftermarket standalone world is the way they deal with boost pressure. And you've kind of already touched on it a little bit as we've gone, but with these more modern ECUs, we don't typically have a boost target table as such. And it's more calculated based on the required cylinder fill in order to achieve a specific torque. Can you just talk to us about kind of how that process goes? So how we achieve a specific boost pressure, for example?
So initially, as you said, because of the torque model, you have an air charge target or relative air charge target or set points. It will convert that into a base boost pressure, and then based on the difference between the expected relative load and the actual relative load, which is realistically how much air is going into the engine, it will either raise or decrease the boost. That's for actually making the set point. So it's a constant feedback loop that will try to adjust your set point so it match. So the air load is matching what you request in the torque model.
I guess one of the more contentious questions that comes up is the pros and cons of a factory controller versus aftermarket standalone. And this is something that I've seen develop over my career. I mean, when I first got involved in tuning 20 plus years ago now, the factory engine management was pretty archaic by today's standards, but it wasn't really needing to do a lot. It was very basic. It was fuel and spark and really not much more. These days now, with our more modern cars, you've got numerous controllers in the vehicle and everything's talking together over CAN bus, which kind of makes this a bit of a moot point because it's difficult, if not in some instances impossible, to take a brand new straight off the showroom floor Audi or BMW and remove the ECU for the engine control and fit a Link or a Motec or a Haltech. You might be able to make the engine run, but that'd be the extent of it. The car's not going to move. So this is, I think, one of the drivers behind the aftermarket world in terms of reflash support for these vehicles. But that's another topic. What I want to know is about the actual running of the engine, because there'll be those on the aftermarket ECU side of this argument saying, my Haltech can run this engine as well as any ECU. But I'm going to guess that the sophistication of even the best aftermarket ECUs probably pales into insignificance compared to the likes of the effort that Bosch and Siemens are pouring into their controllers. So lot of questions in there, but hopefully you get the gist. And can you give us some input from what you see?
Well, I mean, the only pro I see, well, there is two pros here in the aftermarket ECU. The first thing is if you are swapping the engine, for example, it's very easy to connect and have the vehicle to crank. The other thing is all the extra features you get from a motorsport grade ECU, such as logging, special features, all of that work. And of course, you don't need to do any of the definition, but that's clearly about it, because on every aspect, the factory ECU is probably better, because I mean, they've been spending a lot of time with the control, refining the control. The strategy of the factory ECU is way ahead of what we're seeing in aftermarket ECU. You have been mentioning MED9. I mean, if you look at top grade aftermarket ECU, it's not even close to that. And keep in mind that it's an ECU that is 15 years old. So you can clearly see a very big difference in terms of functionality and control. Also, speaking of the control, most new engines are with direct injection. There is not so many aftermarket ECU that have proper control of direct injection. I mean, controlling the pump is one thing, controlling the injector is another thing, but close to no OEM ECU are doing a single injection. Close to no ECU are doing a single ignition anymore. I mean, it's all, with different combustion cycles, like there is homogeneous and a split, and it will always try to find a good balance and have switchover points, like at some up to that RPM, it will do 2-3 sparks, and then it will go single spark. It's completely different. I don't think you can get the level of control of an OEM ECU with an aftermarket ECU for a cost-effective solution. And on top of that, you also need to keep in mind that, as you have been mentioning, the integration of an aftermarket ECU onto a stock platform is something that is extremely complicated. So that's a big con here. I mean, try to run a new BMW or a new Audi with an aftermarket ECU. Just speaking to the rest of the car, the rest of the network is going to take you months. And most ECUs, aftermarket ECUs, have finally been integrating CAN bus, but factory vehicles are not using CAN bus anymore for years. All new vehicles are using like FlexRay or CAN-FD or even DYP, which is Ethernet. So we're really into a completely different technology there. And most control units, aftermarket control units, will probably not catch up before 5 to 10 years on that technology.
All right. Again, lots to unpack from that, but I think probably two key elements that I take away from what you've just said there, which are relevant to this conversation, is, first of all, yeah, you're absolutely right. As I see it, the aftermarket ECU world has lagged significantly behind even what is now quite an old OE controller. And then there's the complexity of integration aspects, which you mentioned, like multiple spark, multiple injection. And I guess from the aftermarket standalone world, what the manufacturers there are also trying to balance is providing a product that will do a really good job of running the engine, give the functionality that we need, but also dumbing it down to a point where the average tuner can still actually get their head around the strategy they're using and actually do a good job of programming the engine and getting it out the door to the customer. And unfortunately, given that I've spent my life in this industry, the whole reason essentially High Performance Academy was founded is because in most instances, even with a fairly basic aftermarket ECU, the average tuner is unfortunately not doing a good job. So this is always the battle as I see it. You give the tuner some really advanced tools and the ability to do an OE level job of control, and basically you're giving them more opportunities to fail. So I think, is it fair, do you think, to say that dumbing it down is almost an essential element in the aftermarket world to be able to get good quality average tunes? So
in my opinion, the factory ECU is doing a much better job at protecting the engine than a aftermarket ECU, because, I mean, for example, if you look at knock control knock control for a factory ECU, it's extremely advanced and extremely safe. So unless you mess up with the knock control, and if you just put some piggy values in the initial timing maps, it's not going to do any damage. It's most likely going to have a huge retardation, but you're going to be pretty safe. While if you go with an aftermarket ECU and first the knock control is not properly calibrated, I mean the filters and all of that, and you input some values in the initial timing map, it will just dumbly apply these values and potentially kill the engine, destroy a piston or something. It's a lot easier to break an engine with with an aftermarket ECU, I think.
Yeah, 100%. I would agree on that. And I mean, when I first got started, knock control strategies in aftermarket ECUs just didn't exist. So that's only something I've seen develop. And certainly those technologies are better in some platforms than others. I'm just interested to dive into that comment a little bit more, where you say that the knock control strategy in a factory controller is so advanced that it's just about difficult to cause damage from knock. What are they doing differently? How does that strategy work?
I mean, it's a pretty big subject, but so what they're doing is, well, of course, there is very different technology, but first, the filtering is very good. That's one point. And what they're doing is that they start to record at a specific angle before you do the ignition. And they are listening for a given window. So in duration, in terms of degree, it's going to be like 40 degrees, let's say. And I mean, the processing behind the way it's comparing against other cylinders, against the average noise of the engine, it's pretty efficient. And the way they do the dynamic regulation, they also have, for example, let's say adaptations. So if the engine is knocking in one specific area at full throttle, then it's going to learn from it. And so the next time you hit that area, it's again going to already apply, let's say, a pre-control or regulation with a negative retardation before the knock event occur. And only if the knock event doesn't occur for, let's say, 5-10 acceleration in that area, then it will start to remove some of this in that adaptation. So for me, I mean, it's just one example, but there is literally dozens of very specific details that we could speak for hours, but it's clearly a lot more advanced than just retarding and blindly reapplying the timing.
Yeah, so the key I've taken away from that is that sort of, most in the aftermarket world, they wait for knock to occur and then retard the timing, and then there'll be some kind of decay where the timing from the map that the tuner has programmed is gradually reintroduced. But essentially, if you've got an over-advanced cell, it's a reactive system, it's not predictive, so knock has to occur in order for the timing to be pulled, whereas you're saying there that the OE world sort of, they learn from that knock event, and if it's repeating in the same area of the map, then it actually starts pulling timing to compensate there so that the knock will be removed, which would be a great way of compensating for dramatically different octane fuel, for example. Would that be fair?
Yes, for example, if you're just imagine that you are at the gas station and by mistake or because of bad luck, you are just filling the wrong gas and then you floor it because you're not very clever. And I mean, you are going to see huge amount of retardation. And keep in mind that when you turn on aftermarket ECU, you're mostly targeting enthusiasts, so people that are taking care of their vehicles. When you're an OEM, you need to deal with every sort of customers, including people that absolutely don't care about the car, don't care about the quality of the fuel they're using. So they do need to spend a lot of time. And also, I mean, not just, I mean, sometimes you don't care, but also sometimes you just don't have access to quality fuel. I mean, if you go to some country, there is only very bad quality gas. And when you tune remotely, it's a big challenge. But I mean, OEM need to deal with that for all customers. So it's a real challenge for them. And I think that's one of the reasons that their protection and the quality of their control is very good.
Yeah, no, it makes sense. I'll just sort of come back to my earlier question, and I just want to just really sort of clarify. There's a couple of things from my perspective that we really need to view. Not saying that one option is better than another, but more a case of understanding the intentions of a current OE manufacturer for engine controller versus aftermarket. The OE controller, as you've just mentioned, they're dealing with people who may not care too much about their engine, so protection is key. So there's a lot of work goes into that, which may not be quite as essential in the enthusiast world. More importantly, though, emissions is a massive driver. So these OE controllers need to be able to really tightly control emissions while optimizing performance. Again, in the enthusiast world, generally, in most instances, emissions is not quite so critical, particularly if we're talking about racetrack applications. So, we don't need to worry so much about that. And my third and final point is what we really need to also keep in mind is when we're looking at the pros and cons, an aftermarket ECU from the likes of Haltech, for one example, that one ECU needs to be able to operate adequately 1,000 different types of engine. You could just about wire that to any port injected engine and probably get it up and running and do a reasonable job of tuning it. Whereas, a modern factory-based controller, the control strategy is very tightly defined around a specific engine platform, and if it needs special functionality or options to do a better job of running that one engine, that's able to be done. So it's probably pretty easy to understand that, therefore it can, in general, do a better job. So I just wanted to sort of expand on that earlier question, because I know you maybe didn't quite understand what I was getting at. Hopefully that's explained things a little bit better for those listening. Now, I want to move on and get a little bit deeper into flashing and bFlash in particular, which we haven't even really touched on it at this stage. And when it comes to tuning an aftermarket ECU, nice and easy. They obviously provide an interface cable or whatever we require to plug straight into the ECU, job done, and we've got it up there and live on our laptop. It's not really the same in the OE reflashing world, and particularly there's options around flashing or reading or data logging via the OBD2 port, which from the tuner's perspective is really clean and nice and easy. That's not always the option, and we can also read and write via bench flashing or background debug mode as well. Can you talk to us about those three options and when one is necessary over another? Does this depend on the controller we're working with?
So as you mentioned, there is more or less three options for flashing. The first one is what we call front door flashing or OBD flashing, which is directly via the diagnostic ports. It's of course the easy method that everyone wants because you don't need to get involved in complicated things. You just need to plug in and connect, which is very easy. But it's not always possible because there is more and more security. And we keep in mind that OEM do not really help us flashing their ECU, so you need to reverse or the control unit access is working. And you have two other methods. The first one is bench flashing. So bench flashing means that you're connecting directly to the ECU but without opening it. So let's say directly on the ECU connector, it gives us access to work canvas. So, for example, there is no gateway, no filtering of the bus, but it also gives us access to other pins, and then we sometimes are able to enter other modes like factory flash mode that they're using directly at the factory. And then the lastest method, which is the most complicated, if I can say, is what you mentioned as PDM, but let's call it boot mode. So boot mode requires that you open the ECU and do have a direct access to the CPU. So sometimes you just need to connect nicely because there is a debug port that is designed in the factory PCB, but sometimes you really need to mess up with it and connect some wires to enter some specific modes. So that mode is really the one that is designed by the CPU supplier. So it's really the lowest level you can get access to a control unit. The bench mode, on the contrary, is more something like, let's say, an ECU supplier mode, like Bosch or Siemens or whatever. And the OBD is more like the OEM mode, so BMW or VAG. it's 3 different communication methods that are all have pro and cons.
One of the big cons, I guess I would see with the BDM method is we physically need to open the controller to get access. And then just as importantly, it needs to be resealed, because these late model controllers almost exclusively now are engine bay mounted, where they're exposed to moisture. So what can you give us a really brief rundown on what's actually involved in reliably opening and resealing a factory controller?
The way I'm doing it is using an heat gun. So of course, remove all the screw first, which is let's say the step one.
That would be helpful.
Yeah, that's the step one. But then I'm using heat gun and brake cleaner. So brake cleaner is actually helping to, let's say, dissolve the sealing. And with a small cutter and some screwdrivers, you actually able to open the issue quite nicely. And when you're done, what you need to do is using a sealant that is non-conductive. Because you are in the presence of electronic components, you don't want to have something that is able to conduct any sort of electricity. It's also sometimes best used that before you're actually manipulating the PCB, so have a direct contact with the CPU, you're using some electrostatic gloves or things like that, so you're actually not doing any static discharge on the board that can actually destroy it.
Because these are expensive controllers, so get it wrong and you're going to be up for a fair expense to replace it, correct?
It's going to be a good experience. I mean, we all have broken controllers, because when you start tuning a car, first, most people are not using the right tool the first time. That's the thing. You always start with the cheap tools or the tools you have seen on the internet, and sometimes this is not just the right tool. And with experience, you are using the right tool, and it's getting a lot better. But it's exactly the same as opening the ECU that we just mentioned. The first time you do it, it's probably very messy for most people, because you don't have the experience to do it properly, and you will use a lot of force or too much heat or whatever. And then when you are doing, let's say, 5, 10, then you get the trick of how to properly do it, and it goes a lot better.
No doubt. Now, I can assume that these factory ECU manufacturers and the OEs that they're going into, the OE manufacturers' vehicles that they're going into, are probably not super keen on us in the aftermarket getting in there and messing with their pride and joy, potentially messing up emissions and also causing potential warranty claims or reliability issues with the engine. So I'm guessing you kind of already alluded to the fact that they don't exactly sort of jump on the phone to you and help you out, telling you how their controllers work. Are they making your life more difficult in terms of getting access? You've talked about encryption broadly as well. So how hard is it getting with these newer controllers for you to be able to access and modify them in the aftermarket?
I don't think they make it very hard for the, let's say, the tuners, because I think there is some very decent tuners that care of the emissions and all of this. I think the main reason for the complexity is the risk of thief, car stealing. So, of course, if you have the access to flash the ECU, you could potentially have the car to start, and without the key, for example. And all that kind of things, they are spending a lot of time into making it more secure, so they're avoiding any big issues with that. You have been mentioning warranty, but most tuners are, I hope, informing the customers that once you tune a car, you're losing the warranty and you're on your own. And I think most people are tuning car after the warranty period is gone. But just for your information, most brands have been incorporating something called tuning detection. And tuning detection is actually some sort of flag that is reporting that the vehicle has been modified. And so they use it to deny the warranty.
I think I'm glad you brought that up, because this is a question that we do get a lot. Is, will flashing the factory controller void my warranty? And I think there's a misconception out there that because you haven't replace the factory ECU with something aftermarket, then you're good to go if you manage to damage the engine. But that's not going to always be the case, correct?
That's not the case. I mean, probably a few manufacturers do not care or don't have the tuning detection or whatever big process in place. But the general rule is that once you tune a car, you're losing the warranty. You're not losing the warranty on the vehicle. You're actually losing the warranty on the powertrain. But everything else, the suspension, the electronics, the drive, whatever, will still continue to be under warranty because, I mean, it's mandatory.
Now, in terms of another aspect we've sort of seen in terms of like later model controllers, it's not always possible to read the calibration data directly out of the controller. You can write to it, but you can't read from it. Can you tell us about why that is the case and how the likes of bFlash get around that?
Well, so the reason is simple. I mean, most manufacturers don't need to actually read the content of the ECU. They know exactly what is inside. I mean, it's their own calibration, so they don't see the need to provide us a nice way to read it. Some does, but it's clearly not the general case. The way we get around it is, well, either we're using lower level programming, like we have been mentioning, such as bench programming or boot mode programming, that is giving us more access, and then we can extract the data. Or a different method is just having access to factory files. So, for example, if you are reversing the factory flash tool or going to the dealer and reverse engineering the communication of the flashing process, then you will have access to that data. Of course, it's not. I mean, many people, just like we have been mentioning definition, they were expecting that the data is some sort of clear data, just like it's going to be a switch and you have like, oh, do this or do that. But no, the data is clearly not clear. There is still a huge amount of reverse engineering required to actually decrypt the data and interpret the data.
So one option, if you can't read, as you mentioned there, you can essentially start with a base file, which was that stock calibration. So if you're in that situation, the only downside, I guess, is if you've got an existing calibration that's a tuned calibration, you're going to not be able to read that data via OBD2 at least anyway. Is that correct?
Yes, that's correct.
So you'll be reverting to essentially a stock calibration starting from scratch.
Yes, that's correct. So you will not see what is inside the control unit. You will just know that it's, let's say, not original, but when you are using what we call a virtual read, which is something we have been either previously dumping by bench or something like that, you will actually have a stock file which will not include the code change or the calibration change of the previous tuner.
Which is, I guess, good in one way for protection of existing calibrations. The other thing I would say, and this isn't an across the board, but something I do see quite a lot in the aftermarket world, we always recommend to actually build your own map from scratch rather than working off an existing calibration, because more often than not, at least in the aftermarket world, you're probably going to be working from something that's got some errors baked into it. So when you're forced to sort of start from a stock calibration, it avoids that chance that the last tuner who worked on it's actually made some fundamental error that you may not initially pick up. So in a lot of ways, kind of just forces you to do the job, as I sort of say anyway, the right way from the get-go. Now, let's sort of jump into bFlash, because we sort of, again, haven't really talked too much about what bFlash is. So give us the sort of 30,000 foot view of bFlash as a company, as a product. What is it and how does it work?
So bFlash is a product we have been designing a few years ago to answer our own needs, actually. As I mentioned, we have been stuck with reflashing late ECUs in the past, and we decided to go with our own tuning solution. We also have been in the decision to include other features such as diagnostic and data logging that are, fundamental for a tuner. So we have been designing everything from the scratch. We have been looking a bit at what everyone was doing, aftermarket tools, but also OEM tools, to see pro and cons of each tool and try to come up with a solution that could cover most of the requirements. You never really cover 100% of the requirements, but you can cover most of them. And we have started to include flashing solution for European vehicles. And when we have been at the SEMA show in 2019, I think, we had a lot of requests for GM platforms. So we started to spend a bit of time on GM platforms as well and adding support for these vehicles. We are continue growing. We try to include more and more platforms. We're currently working on new Toyota. For example, the Yaris GR, it's one of the platforms that we're spending a bit of time on at the moment.
Before we talk about the Yaris, because I'm interested in diving into that, it's become a pretty popular little car for modification at the moment. In terms of that tool, so reading, writing, diagnostics, data logging, great. So does the tuner using your tool still need to do the reverse engineering themselves, or are you able to provide essentially a definition, or more likely what it's probably called in the OE flashing world is a map pack? Can you talk to us about what is required from the tuner?
So when you read the file with the bFlash, you're essentially getting a binary file. So the tuner needs to have an editing software. There is plenty of editing software. You have been mentioning WinOLS earlier, and that's what most of our customers are using. So we don't provide any definition. You're actually on your own for that part.
Okay, so it's really important to understand that this is just the case of getting that raw binary file out of the controller, and then you can do something else with it in a third-party platform, and then once you've made your changes, then bFlash can then write that back into the ECU.
That's correct. This is actually a big difference, and it's a technical decision we decided because most of our customers in Europe are working that way forever. Most American and for Japanese cars, for example, for Subaru, Evo, all of that, you have an all-in-one solution that is doing the definition inside the edition software. For European vehicles, it's clearly not the case. Everyone have different way of doing definitions. So everyone prefer to have a raw binary file that is easier for them, so they can use any editing software they want.
In terms of those who want to get into this world, maybe tuning European vehicles, and maybe they've purchased a product like bFlash, are there solutions for them commercially being able to buy definitions so that they don't have to do that heavy lifting of actually reverse engineering the controller themselves?
There is plenty of people that are selling definitions for different platforms. It all depends on what platforms you decide to work on. We have one of our company that is providing that kind of services. We also provide, let's say, base maps. You also always need to adjust these base maps to switch your fillings and, domestic tuning particularity. But yes, there is clearly a lot of solutions for definitions for different platforms. So if you just go on Google and go with whatever platform plus map pack, you will probably find something you need.
Okay. I just wanted to clear up that while we have been talking about this reverse engineering, if those listening want to get into it and that sounds like it's a bit too much for them to get involved with, there are other solutions. And with those map packs, essentially someone else has defined the raw binary file, and then you also still have to revert to understanding how that controller functions, but at least you're going to have access to maps that look and feel like we'd expect coming from a standalone tuning world. So I just wanted to clear that up. Now, the GR Yaris, so you just mentioned that, and we talked a little bit before we started this interview about the fact that you're bringing out support for this. It's a platform that I've seen evolve quite quickly, and at least in the Southern Hemisphere, there's quite a few people now making pretty crazy amounts of power. We've just been to World Time Attack recently, and there's a Yaris running in Club Sprint that an incredibly fast lap time for the sum of its parts. We've seen them running 10s on the quarter. I think probably in excess of 500 horsepower from a 3-cylinder turbocharged engine is pretty insane. Up until this point, the only option for full tuning was from Motec, and I believe maybe Cyvex also have a plug-and-play solution, both of which become relatively expensive options. More recently, there's been some sort of murmurings about support of the Oem controller. So can you talk to us about what's involved with bFlash now supporting the GR Yaris?
Well, first I want to say that I think the Yaris GR is a nice platform. Most people that are enthusiasts have seen that, for example, there is no more Lancer Revolution. The WRX is not sold in Europe anymore. For example, there is no WRX, no STI anymore. So it's clearly, it's the GDM car that is getting the legacy of that era that we're finally getting. No, we are getting, not in Europe, unfortunately, but in the US, we are getting the Corolla GR. So more or less the same engine. So I think it's a new challenger, and Toyota is doing a great job there. So I think it's a good thing. Regarding Oem Ecu Tuning, so yes, it's something we're working on at the moment. It's evolving quite a few technical challenge. It took us a bit of time to figure out how to reverse it and how to flash it. But know that we're going to get a solution for it. It's going to be a lot easier. You won't need to replace the factory ECU. You could directly reprogram the factory ECU. It will have, of course, all of the integration you can have from a factory ECU, so nothing will change for the cruise control for all of these features, which is very practical. And also, the cost of the solution will be a lot cheaper for the end user than replacing the ECU. It's also a lot easier.
Just a couple of things you mentioned there, and this is definitely not a platform that I've had any personal experience with, so I'm not claiming to be an expert on it. I talk to a lot of those tuning as well as those making products like the Motec plug-and-play ECU, and you mentioned cruise control. And from what I understand, that is probably one of the factory elements that likes of the Motec M1 platform could not incorporate. I believe it's something to do with some security coding and the way that radar cruise control functions. So that's something that they couldn't replicate, which for a race car obviously doesn't matter at all. But if you've got a modified street car, I know that radar cruise control is really, really nice. So that's just one of the downsides to moving to that standalone platform. Now, yes, as we mentioned earlier, there are some advantages with the standalone in terms of some of the motorsport specific functionality and data logging, but for probably 75-80% of people who want to modify this platform, that's probably irrelevant. And I just wanted to focus on that price point because I don't have a Motec or Cyvex catalog in front of me. I can only go out on a limb and expect that those products as a plug and play are probably running to several thousand US dollars. Obviously, there's a cost involved in the likes of the bFlash product, but once you've purchased that, it's useful for thousands of different vehicles. So essentially, once you've got that, once you have a map pack or an understanding of the GR Yaris ECU and operation, what's the cost to the tuner then to tune that vehicle?
So the first thing to understand is that bFlash is a tool that is designed for tuner and not for end user. We're not making an end user flashing device. We're really targeting pro tuners so they can actually flash their customers in their shop. So that's one thing to understand. The cost of our setup, it's 4,900 euros, including shipping. And we have actually two versions. So we have what we call the master version and the slave version. The master version is actually the pro tuner, and the slave version is actually if you have dealers, let's say. So you can actually remote tune for your dealer, and you can have like a network of dealers, and they will all have your slave tools. It's a bit expensive if you just need to tune one car, but if you're tuning, as you have been mentioning, thousands of cars, it's really opening your market to many brands like BMW, VAG, a lot of other brands is getting a lot cheaper. We're also working, that's something very important because many people don't really understand, because I mean, most people that have been tuning in the aftermarket, they're used to some sort of per vehicle model where they will pay for each chassis number, for each VIN number. In our case, it's clearly not working like that. You pay once upfront, and then you pay a yearly subscription of 600 euros, and you can turn an unlimited number of vehicles. So it's a completely different business model, if I can say.
Yeah, so I probably should have clarified. The bFlash product, as you've mentioned there, it's clearly not targeted as an enthusiast level product where you're going to buy that just to tune your own vehicle. This is a professional level product that a professional workshop would invest in. But I mean, while yes, close to 5,000 euros an upfront cost, it is expensive in terms of tools that give you access to that really diverse set of vehicles. That's actually quite reasonable. And the point I was trying to make is essentially once you've got that initial investment in the product, obviously your ongoing subscription yearly is almost an irrelevant amount in terms of a professional workshop's outgoings. But my point is basically once the tuner has invested in that plus understands that GR Yaris platform, it's free for the tuner to actually then access the ECU and tune it. So, I mean, obviously, therefore, they set their own price point on what they think their tuning work is worth. For the end user, the owner of a GR Yaris, when they're looking at their options of taking their car to a tuner, purchasing and adding an aftermarket standalone versus having the factory controller reflashed, the end outcome is we should be seeing a massive, really significant reduction in the cost, which I think is then going to drive more people to modify their car. And I think we're probably going to see an even bigger explosion in support and modification of that vehicle, which I think can only probably be good for the market in general. And is that sort of a good summary of the situation?
I think it's a perfect summary of the situation. I think we'll see, now that we have, let's say, Oem Ecu Reflashing, we're going to probably see a lot more people making parts for them as well, because of course when you're making it on aftermarket issue, the volume of parts you're going to sell is a lot lower. So we can expect to see people making parts, for them in the near future.
Now, just to sort of come back as well a step, you mentioned that you've been requested support for the GM platform, which is interesting to me because that GM platform, if we're talking sort of the LS in the US, which is obviously the super popular tuning platform, and that's really well supported with reflashing so far. EFI Live and HP Tuners would probably be the big two, but both of those have essentially that per car, per vehicle cost associated with them. So is your requests around support for that GM for these tuners who are maybe tuning 5 or 10 of these vehicles a week and want to get away from that per car platform or model?
Yeah, so we had more or less two kind of requests. The first one was because they did not want to pay a per car fee. So they wanted just to make their own file, their own definition. They were perfectly able to find maps, and they wanted to avoid paying for each specific vehicle. So that was the request number one. And the second thing was, once we started to implement some solution for GM, we noticed that some controllers require shipping to, for example, HP tuners like the T87, which is the gearbox control unit, for unlock. And so, of course, the problem is each time you want to do an unlock, you need to actually ship one TCU there. It's going to take a few days. Then, you have the car that is stuck in the workshop. So they asked us if we can come up with a solution that will allow them to flash directly in the shop. And that's why we have been delivering that solution. We're also working on a bunch of new solutions for GM, but that's for a more long-term solution.
Okay. I'm interested on that note because we've gone through exactly that scenario. We've got an in-house development vehicle, which is the 2018 Silverado with the L5P 6.6 turbo Duramax diesel. And we went through that scenario, which particularly from this side of the world is a real pain, shipping the transmission and engine controller to HP tuners to have them unlocked so we could calibrate them. Okay, so two questions there. First of all, what is this unlocking actually involve, and what? It sounds like you've now got a way of working around that. That's correct.
Yes. So, well, it's. I mean, it's probably we probably did that more than 1 year ago. So yes, as you mentioned, I mean, New Zealand is the case, but it's clearly the case for many other countries. When you need to ship an ECU, probably if you live in the US and you need to ship to someone in the US, it's fine. But when you're living in Europe or in whatever other country and you need to ship abroad, then you need to go into customs and all of this. And it's costly, but it's taking time. They need to inspect the package, all of this. So it's clearly not a simple and easy procedure. So the unlock, what it involves, the problem is always the same. How hard is the OEM locking us? So there is two generation of T87. There is the T87, the normal one, and the T87A. The T87 we could flash it normally, let's say, without any significant protection. And on the T87A, we have been more or less changing everything, and not only the security access change, and it was a more complex 5 byte GM security, but it also changed in the way that we could not read or write without unlocking the control unit. So unlocking is actually the fact of re-enabling the access to read and write that control unit. In our case, what we did is that we came up with a bench solution. The TCU is made by Hitachi. So we came up with a bench solution that gives us full access in reading and full access in writing. So we can actually read the factory content of any T87 and program whatever, either your custom calibration, but we can also perform a programming of an unlock patch to re-allow flashing over the diagnostic ports.
And that sounds like an absolute godsend for those dealing with those controllers, both in terms of a significant cost saving as well as you mentioned, time. I can only assume that this is something that's just going to be a continuing battle between the OEs and the likes of yourselves as time goes on. They continue to throw more challenges your way, and I guess there's enough motivation and money involved in the aftermarket tuning world that you'll continue to find solutions.
Well, it's getting more and more complex, and I think that's one of the reasons people ask ECU to be shipped is because they don't want to expose the solution they're using. And by doing so, I mean, if you don't expose how you're doing it, then people cannot close that back door. And so you're actually buying yourself some time and saving yourself from the risk of seeing your back door closed and then you don't have any solution at all.
Okay, now that makes sense. All right, look, I think we'll move towards wrapping this up, and we've got the same three questions we like to ask all of our guests. And the first of those is what's sort of in the future? What's coming up for you and bFlash? Any sort of exciting directions that you're heading in that you'd like to share with us? Obviously, we've talked about the GR Yaris support, but what else are you sort of excited about at the moment?
Well, there is actually a lot. Of course, we cannot share everything because there is some things that are quite confidential, but we're working pretty hard on the new Bosch protections for locked ECU because, as we have been mentioning, there is more and more security and we need to go around the security. We've been working very hard for the past 2 years on finding ways to go around this. So that's one big subject. The Yaris is indeed a big one as well. And on top of that, we continue to improve the general software for flashing, logging, diagnostic. We just try to come up with more definitions for the fault code, more definitions for the data logging, so we can actually provide quality tool for our customers.
Okay. I can only assume with the support of the Yaris, the Corolla GR is going to also probably see some support when that becomes a bit more available in mainstream?
I think that's a very good question. We know it's the same engine, but we don't know yet if it's going to be the same control units. We don't know if it's going to be the same security. So I think it's a bit early to speak on that.
Sure. Okay. Of course. Next question is, given where you are in your career at this point, everything you've learned, everything you've done along the way, and inevitably the pitfalls that you've probably seen and gotten over, is there any advice that you'd give to a younger version of yourself to sort of help fast track your career and get you where you've got to quicker?
Well, the first thing is you need to love what you're doing. I think it's the key point. If you don't really like spending time on control units, on engines, on all of this, it's going to be very challenging to learn. Then, more and more, we're seeing, more and more electric vehicles, less and less petrol vehicles. We see more and more hybrids. So if you're considering working on vehicles in future, it's probably a good thing to start actually learning on electric vehicles.
Yeah, I think that's a given, really. Unless you've been hiding under a rock, it's pretty hard to not notice that momentum has definitely swung in the direction of EVs. And here at HPA, it's something that we're looking to bring out some course material and support on in the near future, because I think internal combustion engines are always going to have a sort of a place in my heart, but the direction of the future is clear, so I might as well embrace it, I think.
We have been seeing also change in the past. Look, people were tuning carburetors years ago. No one is tuning carburetors anymore. Everyone went to full injection. We have been to post-fuel injection or direct injection. The thing with our industry is that it's constantly evolving. The automotive industry is evolving all the time, and we really need to continue in that direction, follow the progress, and evolve with the technology.
You make a really good point there, and actually I'll just speak to that for a moment, because that's something that I saw when I was first just getting started in the industry and learning to tune, and something that I've tried really, really hard to avoid myself. And what I saw was a lot of the existing tuners, when I was just sort of coming up and getting started, was they would get to a level of comfort, I think, with the technology that they were using. And that might have been carburetors, or maybe it was an older, very basic aftermarket ECU. And they'd sort of top out at that level, and then technology would take another leap forward, and they'd not want to go through the trouble of learning that new technology. So, slowly their market size would diminish as everything moved on. And I sort of saw that happen to a few relatively prominent people in the industry here in New Zealand. And I sort of took note of that and wanted to make sure, to the best of my ability, that didn't happen. So I'm always trying to keep abreast of new technology, seeing what's happening, and I really make a dedicated effort to never kind of close down and stop learning. But for me, that's also what keeps me passionate about this industry. As you mentioned, there's always something else coming up, and there's always something new to learn. You never know everything, and that's why it's always so exciting to be involved in the tuning industry. Now, our last question for today: if people want to follow you, find out more about your products, where are they best to do that? You've got some social media locations they can head to?
Well, most likely Instagram or Facebook at bflash.eu for both. We're there. We'll try to answer. Most likely not me, most likely the sales team. But if you reach out, probably I can speak.
Perfect. Really appreciate your time today. It's been a fairly in-depth convo that's probably going to require a few people to go back and re-listen to it again. But particularly for those who have listened, who are interested in learning more about the OE reflashing world, I think there's been some great information in there. So really appreciate all of the information you've given us. Thanks again for your time.
Thank you again for your time as well.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.